Welcome to the New Books Network.
Hi everyone, and welcome to New Books Network. I'm Galina Limorenko, doctoral candidate in neuroscience with a focus on biochemistry and molecular biology of neurodegenerative diseases at EPFL in Switzerland, and I will be your host today. Today we'll be talking to Frank Close about the new book, Elusive: How Peter Higgs Solved the Mystery of Mass. The first major biography of Peter Higgs, revealing how a short burst of work changed modern physics. A revelatory study of both a scientist and his era, Elusive will remake our understanding of modern physics. Well, Frank, welcome to the show.
Hi.
So how are you? How is your week going?
Well, good news and bad news. I mean, I had COVID about 5 weeks ago, and I'm still trying to get rid of the coughing. So I hope it doesn't start in the middle of our chat.
Oh boy, I hope you feel better.
Yeah, oh no, I feel fine. Otherwise, it's just something that happens at random.
Oh, all right. So can you tell us what you do?
Well, I'm a theoretical physicist, a particle physicist, but I spend a lot of my time writing.
And how did you get interested in physics?
Well, as a child, I was very interested in science. I didn't like chemistry because I could never remember. It seemed to be a lot of facts, whereas physics was more a question of why do things happen the way they do. And I always wanted to know why, wanted the explanations. So I suppose that's why I got into physics. But it's the fact that I'm a physicist that I've been writing books around physics for a long time, for the general public primarily. I've got very much interested in the history of physics and science, the latter half of the 20th century, having lived through quite a bit of it myself, I suppose. But this latest book, Elusive, is about Peter Higgs, the creator of the Higgs boson particle that was discovered 10 years ago in 2012. And the fact that this is what I was writing links to who I am, in that I've been a physicist in the same field as Higgs for the whole of my career. I've known him as a colleague and as a friend for maybe 20 or 30 years, I should think now. And the fact that when the Large Hadron Collider at CERN was being planned 30 odd years ago, time flies, with its goal, at least in the public's mind, to create the conditions that could produce this predicted particle that was so key to modern theory. The idea of having Peter Higgs popularize this was mooted, but Peter is a great scholar, but not the sort of person who easily goes onto the stage and speaks to people. And so what happened was that I would go on stage and interview him so that he would sort of develop the story with me as an interlocutor. And this is the first time I'd done that. Our first chat together was before the boson was discovered. I happened by chance to be at a summer school with him immediately before the boson's discovery was announced. And we can talk about how he got called away from Sicily, where we were, to go to the meeting in Geneva where the announcement was made. Then I interviewed him again afterwards. And over a period of about 3 or 4 years, we had several conversations like that. And I began to realize that I was living through history here and talking to this man who he's very quiet, very modest. And I thought, well, I can tell his story because this is the thing that I have been working with alongside him. And so the idea perhaps developed around then. It really matured about 3 years ago, just before the pandemic hit. And that is how the book began. I called it Elusive for two reasons. One, it took 48 years after his first prediction that this particle should exist before it was possible to produce the technology that confirmed it. So the particle, the Higgs boson, has certainly been very elusive. And he himself is a person who is very elusive. That the day that the Nobel Prize was announced in 2013, he disappeared. Nobody knew where he was. The Swedish Academy couldn't find him. And they delayed the announcement for half an hour until eventually they went ahead anyway. So Peter Higgs also is elusive, so doubly elusive.
Oh boy, difficult to catch.
Yes, it's not easy. The fact that he doesn't use the internet at all. He doesn't use a mobile phone. Um, the only way to interact with him, other than visiting him, which of course during the pandemic was not possible. He lives in Edinburgh. I live down in Oxford, which is about 400 kilometres away, was by either writing a letter, but even the mail wasn't being delivered during the pandemic. So I would telephone his landline. He doesn't answer. He worries about the media following him and so forth. So he would then pick up the message on the landline. We would agree a time for him to call back, and then we would chat for a couple of hours. And through the 12 weeks of the lockdown in Britain, we chatted for about 25 hours in total, 2 hours a week. So I would have these long chats with him. I would be transcribing them and developing ideas. And so quite a bit of the structure of Elusive emerged during the lockdown. I think those weekly chats helped keep us sane. I mean, in Peter's case, he is now 93 years old, lives on his own in the third floor apartment in the old town in Edinburgh. Because this is a classical old building, it is not allowed to have an elevator installed in there. So he has to climb up 84 steps, which I noticed was one for every year of his life at the time when he won the Nobel Prize, which he still managed to do. So I think probably we helped keep each other sane during that rather strange period. So the whole book, putting the book together turned out to be Elusive. I hadn't anticipated how apt the title has been.
So before we get into nitty-gritty of the book, you're in a very unique position to tell this history, really. And I was wondering, how easy or difficult is it for you to reconcile your scientific career with writing? What would you say to our student listeners that might be interested in, writing about the history of science, for example, of their fields?
Well, the first question is to be quite clear why you want to do it. Quite a few people, come to me and they say, well, they want to write a popular book about physics or whatever, and because they've heard that somebody has written a book and it's been a bestseller, they've seen Steven Weinberg's First 3 Minutes, this, that, and the other, and they think that they want to write a book and sell, 1 million copies or so forth. So what I say is, look, go into the local bookstore and look at the shelves there, and you'll find many books on our field or on other areas of science by people you've never heard of, book titles that you've never heard of. So first question, why is your book going to stand out on those shelves? On the other hand, you might discover while looking at all of those book titles that there is something missing. So if you found a sort of a niche to be filled, then maybe there's something to go ahead and write, if that's the reason you want to do it. If you want to do it to make money, you've got to be expected not to. Really, you've got to want to do it because you want to do it. Now, in my case, I have been writing popular descriptions of science now for many years, and I find often that, for example, this area where Peter Higgs is working. The area of particle physics that I specialized in dealt with the nature of the atomic nucleus and what's called the strong force. That is not the same area that Peter Higgs worked in. So in part, when I'm writing a book like this, it is my opportunity for the first time to really learn and get into what it's all about. And so it perhaps ends up that I write a travelogue in a way, my particular journey into trying to understand something. And hopefully the reader then joins me in that journey so that the reader also picks up something about the science. That's when I'm writing a book where I'm trying to bring the concepts of science across the reader. This book was rather different. Because I had known Higgs and realized that this was a very singular story in the history of science, and that I was in this unique position, I initially thought that I would write Higgs's biography. And that was 3 years ago what I thought I was going to do, but all projects develop as you get into them, and it quickly became clear that a biography of the Higgs boson was actually the real story. The background to Peter Higgs himself is also there, and it's very important to understanding the nature of the man and how he's reacted to the media that have hounded him in his perception. He doesn't like being thrust into the limelight. I'm sure as we discuss his early life, we will see the...
All right, so let's dive into the book. And then can we start with the very basics? Then could you kind of give us an overview? Who is Peter Higgs?
Year-old Nobel laureate, famed for being the man behind the idea of what we call the Higgs boson, and why that is so important we can discuss later, but that's who he is. But he was born in 1929 in Newcastle in the north of England. His father was an engineer for the BBC. The BBC is 100 years old this year, and his father was an electrical engineer with them. The background, though, when one is trying to understand, I think, the person, it became clear to me, I thought, well, what the public want to know is, what is it that Peter Higgs did? That's one side of the story. But why is it that it was he that did it and not somebody else? So I really wanted to understand quite what his family background was and where he came from. So, for example, his father had been in the First World War and had been absolutely appalled by seeing the Padres, the supposedly men of God urging troops over the top to go and kill Germans and so forth. And he felt that this made the Ten Commandments negotiable. And the result of this was that his father became totally and utterly disillusioned, not just with religion, but with life in general. And after the war, he married the sister of one of his friends from the trenches, and the father was so disillusioned he didn't want to have any children at all. But as Peter Higgs told me, his mother said to him that she had managed to interfere with the traditional method of contraception, as a result of which Peter was conceived and born, their only child, which was fortunate for him, obviously, and for us. So that was the sort of background. Peter, as a child, was quite sickly. He had very bad eczema, so much so that when he was put into bed at night, his arms were encased in cardboard tubes so he didn't sort of scratch himself. He had asthma. He had double pneumonia. We're talking 1930-ish here, a long time before penicillin. And so he didn't start school at the age of 5. He was home taught for a year. And he was not allowed to play with the other children because his parents had the impression that exercise brought on the asthma attacks. So he had a very isolated childhood. Now, he was taught numbers and reading, and I suppose that loneliness in its way both led to a love of scholarship, because that is clearly what he is as an intellectual, a person who loves to read and dig and get deeper into things so he can completely and truly understand the nature of them. So that was one side of his character. The other one is, I think, that being an isolated child, and as well as being an only child, led to him being the person he became as a man, which is shy, withdrawn. He is at ease in the company of people that he knows, but he doesn't like being in crowds or large groups. He likes just to be left to his own devices to get on with things. And as you can imagine, as we'll talk about, I'm sure, later, when the Nobel Prize was announced and everybody was wanting to know Peter Higgs, it was just almost too much for him. So that's the early Peter Higgs, the child. He went to school. Well, the family were initially in Newcastle. They moved down to Bristol in the southwest of England. And they lived there through the war and afterwards. Peter went to school in Bristol eventually, and at the age of 11, the high school he went to was called Cottam School, which happened by chance to be the same school that Paul Dirac, the physicist and Nobel laureate, went to. And Higgs noticed Dirac's name on the honours board in the hall, Paul Adrian Maurice Dirac. I mean, a very unusual name. And he wondered, what had this boy done? And so that was his first insight in the fact that the school had a physics hero. And that, I think, was part of his original interest in becoming a physicist. The war then happened, the Second World War happened, and he was around 1945 in the final year at school preparing for university and was horrified when the news of the atomic bomb explosions took place, to realize that the subject that he was in love with was being used to create these awful weapons. And he said he almost quit there and then, but then discovered that the two professors in Bristol University, Cecil Powell, who later won the Nobel Prize, and Neville Mott, also a future Nobel Prize winner, gave a couple of public lectures very soon after the end of the war about the atomic bomb, insofar as it was possible to know what had gone on, because it was still highly secret, and also the new possibilities of nuclear power and other uses of it. And so Higgs went along and heard those two talks and discovered from the talks that the possibility of using nuclear physics to do things and the new science that was beginning of what became particle physics, that was really when his career choices were set.
So then what field did he choose to study when he went to university and further education?
So he went to university in London, to King's College London, and he did his undergraduate degree there in mathematics primarily. He was, and I would say actually is, primarily a mathematician who uses the tools of mathematics and applies them to the physical world. So he studied mathematics as an undergraduate, and he graduated in theoretical physics because he also was doing physics courses. While he was there, he met a fellow student called Michael Fisher, and became great friends with Michael Fisher. And Higgs said to me, this was the first time in my life that I met somebody that I knew was smarter than me. And Michael Fisher himself became a great physicist and almost won the Nobel Prize. The fact that Fisher was highly tipped to win the Nobel Prize after having had great accolades, and then to everybody's astonishment, not least his, when the prize was awarded to one of his collaborators, but Fisher wasn't included, was totally devastated. And I think that experience may have some relevance for understanding Higgs's running away the day when his Nobel Prize was coming around, but we can get to that in due course. So that was Higgs as a student. He graduated and started to do research in applying physics to biology. We're talking here now 1952-53 time. The discovery of the structure of DNA, I think, was around then, 1953 or so. Just down the corridor from where Higgs was doing his studies was the team at King's College London, Rosalind Franklin there, who were, along with Crick and Watson at Cambridge, discovering what became known as the double helix. And if anybody has read the book about the double helix by Jim Watson, one sees the intense rivalry there was between the Crick and Watson team and the King's College London team. And so Higgs was on the periphery of that in his first student project, doing mathematical studies of helical molecules. And he wrote a paper with two other people, which apparently made quite an impact in that field at that time. I say that for two reasons. One, that is the only paper in the whole of Higgs's life that he wrote with anybody else. He only wrote a dozen papers in his total career, which is very, very small. And they were all, apart from that one, written solely on his own, which again, I think shows you that he is elusive in many ways here. So that is what he was doing in the 50s, but his heart really was set to become a particle physicist. And by 1960, he managed to change fields effectively and was offered a lectureship at the University of Edinburgh. And he moved to Edinburgh in 1960, and that is really when the career in particle physics began.
So can you give us maybe a short overview? What does particle physics study?
Well, in 1960, what particle physics was doing, let me be a bit more general. Historically, particle physics is trying to get deep inside the atom, deep inside the atomic nucleus to find what the basic fundamental seeds of matter are. In 1912 or so, Ernest Rutherford discovered that the heart of the atom contained a massive nucleus of positive charge. And by the 1930s, they knew that this nucleus consisted of protons and neutrons, two types of particles. Post-war, in cosmic rays, the analysis of cosmic rays revealed a lot of very strange particles that nobody ever dreamed of, things that didn't seem to have any role here on Earth. And suddenly it became clear that in addition to the proton and neutron, and also the electron that whirls around on the outside of atoms, there were lots of particles. And by 1960, particle physics was in a total quandary. Far from there being a literal handful of basic particles from which everything was made, they were just proliferating like crazy. And the need for a theory to understand them was absolutely overwhelming, but there was no real progress. People were trying every which way to build theories, and some were crazier than others, but none of them really worked. So that was the environment into which Higgs began in 1960. Particle physics today, I don't know if you want to wait until we get onto later eras, but roughly speaking, in the 1960s, many things happened, one of which was the discovery that the universe began in a Big Bang, and it was incredibly hot during that Big Bang, and the realization that by smashing particles together in machines like at CERN in Geneva, one could create in a very small volume for a brief moment the sort of heat energy that the universe itself experienced in the first trillionths of a second of the Big Bang. We were able to replicate the physical conditions of the newborn universe and start investigating where matter came from, how it appeared, and so forth. And that is much more what particle physics is today. And as we will see, that is really what the importance of the Higgs boson is all about. But in 1960, particle physics was trying to understand the basic seeds of matter and was getting nowhere.
So it was mostly theoretical because there was no way to test it.
Well, in 1960, probably almost the other way around. In that there were ways to test it. What had happened was that post-war, people had been sending balloons up into the atmosphere where we're being bombarded all the time by cosmic radiation. And as these cosmic particles smashed into the atoms of the upper atmosphere, they broke the nuclei of those atoms up and produced these transient new particles. And from that came the idea of replicating that on Earth by building machines that made beams of particles, if you like, cosmic rays that we could control, and smashing them into big targets. In other words, dense targets of matter rather than the diffuse upper atmosphere. And rather than leaving it to chance, cosmic rays come and do what they do, we could design these things to try and investigate specific things. So experimentally, things were moving along very fast. In fact, that was the problem. The experimentalists were discovering lots of things, but the theorists at that stage were not able to bring any sense of order to it.
So what was Peter Higgs working on during that time?
Well, actually, during the mid to late 50s, when he moved to Edinburgh in 1960, his interest had actually been in gravity, in general relativity, which is a subject which is even today highly esoteric and has had relatively little progress in it. But he did make some sort of small level impact in that the small group of people around the world who worked in that field had recognized him from a couple of papers that he had written. And as we will see later, due to that, one of these people invited him to take a sabbatical in North Carolina, at the University of North Carolina in Chapel Hill in 1966, at which Higgs would write his seminal paper. We can come back to that in due course. He had been working on general relativity, as a result of which he became fascinated by a particular piece of mathematical detail. It goes by a name called gauge invariance. It doesn't matter what it is, it's just a label. It's a piece of maths that is very critical when you're dealing with general relativity. And so Higgs became sort of quite expert in this concept. Now, it turned out that when he made the transition into the theory of particle physics in 1960, moving away from gravity and trying to understand the other forces, in particular, the strong force that holds the nucleus together was the one that people really were trying to understand, because this myriad of particles all seem to be bursting forth from the atomic nucleus. And so we were trying to understand, well, they were trying to understand the strong force that binds the nucleus. So that is what Higgs set about. And among the various ideas, there was one that looked very promising. I won't go into the detail, it's not relevant, except that there was a technical aspect of it that seemed to be like a brick wall, that there was a showstopper. Nobody could get through this problem. And one day, Higgs saw a paper that somebody had written where they thought that they had been able to get through this problem if you ignored relativity. Now, Einstein's theory of relativity is critical when you're dealing with high energy things like in particle physics. But if you ignored that, it turned out this person found a way to get through this blockage. However, this person also commented that the way they had managed to get through the blockage would not apply because no theory with relativity had the particular magic feature. And Higgs immediately knew of a counterexample to that by the chance that he had been looking in detail at things for 2 or 3 years. He suddenly realized that he had seen a counterexample to what this person claimed, that it was possible in principle in relativity to get through this blockage. And he wrote a short paper. It just took him about a weekend to sort it out. And he wrote a short paper in 1964, which demonstrated that it was possible to get through this blockage if you included the theory of electromagnetic force in there, a thing that nobody had taken into account. Everybody was so focused on trying to describe the strong force that binds the nucleus that only Higgs realized, but what if you also at the same time include the effect of electrical forces? And it turned out that that would be the way forward. So that was his first paper, and nobody took any notice of it. He then wrote a second paper because he had found the way through the blockage, but now he wanted to work out what would actually happen when you included that in your theory. And he found the lucky strike, if you like, that in getting through the blockage, he found that he'd included the effects of the electromagnetic force. Now, I should just say one thing, that the electromagnetic force in quantum field theory is described by being transmitted by little particles, photons, the particle bundles of the electromagnetic radiation. And Higgs, the photons are massless. They travel at the speed of light. They are light. They have no mass. And the mathematics in Higgs's formalism showed that, surprisingly, by getting through this blockage, the photons would gain a mass. Now, that was tantalizing because photons don't have a mass, except in some unusual cases like in superconductivity and so forth. But by and large, Higgs had found a mathematical solution to a problem. The mathematical solution had a consequence. It had a consequence which seemed to have no relation to the physical world, but there you were. But there was one further feature of all of this, which is that the way that he had got through this blockage and done all of this had made an assumption that the vacuum can never be empty, that there is something always in the vacuum that you cannot turn off. This has become known as the Higgs field. And I've told you almost as much as we know about it. I mean, what it's made of, we don't know, but he made this assumption. And the mathematics works if you make that assumption. And it turned out that around the same time, within a couple of months, 5 other people independently had made the same discovery that you could do this mathematical trick. But of these, only Higgs made the point that if we are really immersed in this strange stuff that we've all had to assume, you ought to be able to do an experiment to prove the facts. And he drew attention that under certain circumstances, you could make this bubble up into particles, which we call Higgs bosons. So that was where we were in 1964 to 66. These people had found a way forward mathematically. Higgs had pointed out that with this, you might be able to test it experimentally, and nobody took the slightest bit of notice because it had no obvious relevance to anything at the time. Higgs tried to apply his theory to the strong force that binds the nucleus and got nowhere. He visited the States in the summer of 1966 and talked to the brilliant theorist Steven Weinberg, who had also been trying to apply these ideas to the strong nuclear force and was getting nowhere. And so Higgs at that point gave up. And although the story is going to have a fascinating future, Higgs was no part of it. Higgs basically dropped out there and then and didn't do anything at all of any significance in physics. I think he only wrote 2 more papers in the whole of his career. Weinberg, however, famously was driving to work at MIT one day when he had a flash of inspiration. As he described it, he said, "I suddenly realized we've been applying the right idea, but to the wrong problem. They've been trying to apply this to the strong nuclear force and it didn't work. But there is another force at work, the force which is called the weak nuclear force. It gives rise to a certain type of radioactivity." And Weinberg suddenly realized that the weak force had all the characteristics that this theory could be applied to. And so in 1967, he wrote a paper showing this fact. And again, that paper was largely ignored for 4 years. And then something happened, and as a result of which, Weinberg's paper has been cited 10,000 times ever since. And the something that happened is really the next part of the story. It didn't involve Weinberg, it didn't involve Higgs, it involved a young graduate student in Holland called Gerhard Toft. So do you want me to go there, or do you want me to ask something about else?
Yeah, go on. It's just so riveting.
Okay, so I'll tell you the state of the understanding of the forces at that time. The electromagnetic force had been known for over a century, and the quantum theory of it, called quantum electrodynamics, had been created in the 30s by actually Paul Dirac, the forerunner of Peter Higgs at the school in Bristol. And by 1947, it was finally showed to be a completely viable theory that satisfied relativity, satisfied quantum theory and everything. And what's even more important, works. I mean, it can describe data to an accuracy of 1 part in a trillion in some cases. And a key reason why this theory works, this is a very technical thing, but is because the photon, the carrier of the force, has got no mass. That turned out to be the key thing. Now, the problem with the weak force, I mean, it's all very well that Weinberger created this theory using this mathematical trick of Higgs. The analogous carriers of the weak force are called W and Z bosons, W for weak and Z for zero charge, but they are both very massive. Empirically, to make this thing work, these particles had to be massive. And that appeared to be the showstopper. That's why people just ignored Weinberg's paper and ignored Higgs stuff, because this is all very interesting mathematically, but the W and Z particles are massive. And that means you cannot copy the maths that had worked so well for the electromagnetic force. Massless photons was key, and you've got something massive. End of story. What happened in 1971 was that Gerhard 't Hooft did a brilliant analysis in his PhD thesis, no less, in which he showed that if you started off building a theory of the weak force, totally by analogy with electromagnetic force, and pretended at the start that the W and Z bosons were massless, had no mass, just like photons, that theory would be viable. And then if you added to that theory the mathematical trick that Higgs and others had discovered, that would produce masses for the W and Z bosons without disturbing this beautiful viability of the whole theory. So suddenly in 1971, their physicists had at last found the golden path. They had found the way to write the theory of the weak force just analogous to that of the electromagnetic force. It was the clue that these two forces are perhaps somehow unified in a profound way. But the mathematical trick that Higgs and others had found was key to it. So after 't Hooft's work, 't Hooft shared the Nobel Prize with his supervisor, who had done a huge amount of work on this himself later in 1999. But following 't Hooft's work, everybody immediately realized this was the way forward. Now, every 2 years, and this is coming like to the end of the first part of the Elusive book, every 2 years there's a big conference, worldwide conference of particle physicists, and very senior figures review certain areas in the field. And the pronouncements, if you like, by those reviews are very similar to the effect that Warren Buffett has in the world of finance. You know, people listen and they go ahead and do what the guru says. And the particular session based around 't Hooft's work was, of course, a very big thing that year. But as Peter said, in the session, they plastered my name over everything. There had been 5 people had this basic idea of how to create mass from nowhere. But by chance, the fact that Higgs had spoken to Weinberg a few years before, and Weinberg had erroneously thought that Higgs was the first person to have had this insight, Higgs's name got attached to a lot of this in a way that Peter felt was not justified, and historically, indeed, was not. I mean, he was one of 6 people who had independently discovered this mathematical trick. As we will see, he did one key further thing, which dealt with the boson, but that's another story. So that, if you like, is the end of the first part of the book. We've got to the stage where Peter Higgs has had this once and once only brilliant idea. He couldn't make it work, so he drops it. But other people have suddenly found that this is the jewel that could make the way forward for particle physics. And at this big conference, everybody is mentioning Peter Higgs's name, and his colleague, one of his colleagues, comes back from the conference, sees Peter in the bar at the university and says, "Peter, you're famous." And that's the chapter title at the end of part 1.
Oh, wow. Science is full of drama.
Yes, it is. It's exciting. It's a human activity. And that's one of the things I wanted to bring out, that science, in a way, science truth is out there. I mean, nature knows the answers and we are trying to find them. So it is a great adventure doing so. And you do it collaboratively. And it is not only a great adventure, it's a very humbling experience when occasionally I mean, let's put it like this. In 1964, Peter Higgs scribbled some equations on a piece of paper. As he said at the time, this summer I made a discovery which is completely useless, is how he viewed it. And then 48 years later, we discovered the Higgs boson, an implication of those equations. Somehow the mathematics in 1964 knew more about nature than we did. It took 48 years before we caught up with the mathematics. It's a very profound thing that is going on in this communion we have with nature. And there's, of course, a lot of competition. As I said, there were 5 other people who had had a similar idea to Higgs during that summer of 1964. 2 of these, Engler and Brout, were working in Belgium. They had the basic idea and published it a few weeks before Higgs. Higgs did it independently next. And then a couple of months later, another group of 3 people published. And so there's 6 of them in 1964. Jump forward to 2012 when the boson is discovered and everybody's speculating about the Nobel Prize. And one of the problems is the Nobel Prize can go at most to 3 people. And so there's a lot of controversy about, well, how do you give it to 3 out of these 6 and so forth? And also there were people and institutions lobbying that their people should definitely be in there, so that science is a pure activity. Scientists are humans. So that is part of the story in all of this.
Okay, so let's fast forward to closer to our day. So how did Large Hadron Collider come into all of this?
Well, this is now part 2 of the 3 parts of the book. So we now, Higgs basically disappears almost from his own story, and others take it up. It's clear to everybody in early 70s that thanks to Toft's work using this particular thing, we've now found the way forward. The first part of this is it all depends upon there being W and Z bosons with mass. And the mass of these things is predicted to be nearly 100 times heavier than the mass of a hydrogen atom. I mean, way out of scale compared with anything that was known in those days. I think the heaviest thing known at that time was about twice the mass of a hydrogen atom. Anyway, by 1983-4, a man called Carlo Rubbia, a senior scientist at CERN, who spent a lot of time at Harvard, and he became later the director general at CERN. But he had the idea of converting one of the machines at CERN so that in addition to whirling protons around a ring, you could create antiprotons, that's the antimatter analog of protons, and whirl those around the same ring in the opposite direction and smash the protons into the antiprotons. Now, anybody who follows Star Trek knows that when matter meets antimatter, they mutually annihilate in a flash of energy. And so that was the idea, to smash these 2 together, mutually annihilate them into a flash of energy, and then thanks to Einstein's famous E equals mc squared, that energy might coagulate as mass, that's the M, and if you're lucky, occasionally into W and Z bosons, assuming that the theorists are right. And wonderfully, the theorists were proved right, that in 1983, the W and the Z bosons were discovered, bang on what the theories said should be the case. So that was very exciting. It gave confidence that we were going the right way forward. So the next stage was to build a machine at CERN, which became known as LEP, Large Electron Positron Collider. Now, the electron is what you find on the outside of all atoms, and the positron is the antiparticle of the electron. The positron, incidentally, was predicted by the same Paul Dirac that was at Peter Higgs's school. There's quite a few little coincidences in this. And the idea of this was they built under the rocks around Geneva a 27-kilometer long ring of magnets to steer electrons one way, positrons the other, and smash them into each other and annihilate. And the point was, by tuning these beams, you could make them annihilate at just the right conditions to produce Z bosons. And over the course of 10 years, about 10 million times Z bosons were made, which enabled them to study the properties of these Z particles very, very precisely. And what they discovered was initially that indeed the theory worked perfectly. But the more precisely they looked at these Zs, they started noticing some subtle deviations from what the theory predicted. And this was exciting because what happens in physics is that although you can only produce particles with masses limited by the amount of energy in your machine, thanks to the wonders of quantum mechanics, it's possible in a way to look over the horizon, to get clues of things going on out there, just out of reach by what's known as quantum uncertainty. And the mathematicians know how to take those things into account. And when they took those things into account, they discovered that these subtle discrepancies between the measurements of the Z bosons features and the theory fitted in with the idea that if there is a Higgs boson, and if this Higgs boson is somewhere out there heavier than the W and Z, then everything will work. So this is now around 83, 84, the W and Z boson have been found. By the 1990s, it's become clear that the Higgs boson looks from theory now as if it really ought to exist. But to produce it, we're going to have a machine that is far more powerful than anything we have currently got. We're going to be able to have to smash together things and produce 1,000 times the mass. In fact, maybe almost up to 10,000 times the mass of a hydrogen atom in one collision. And this is what led to, well, in the States, they designed a machine called the superconducting super collider. It was going to cost them about $10 billion US, and they had started digging the tunnel when Congress then balked and said, no, we can't fund this. What happened in the States was a beautiful example of the politics, which I also discuss in this section of the book. So I'll just tell you how it works. I mean, various states in the United States all wanted to have the super collider built in their state. And the senators were all very positive so long as their state was still in the running. Then eventually the decision was made that the site would be chosen in Texas, at which point almost everybody except the senators from Texas thought it wasn't such a good idea after all, as you can probably imagine. And so the whole thing was stopped. And so now the Europeans said, well, the only way to proceed is for us to build a machine, and that's what became the Large Hadron Collider. The idea being that we've got this 27-kilometer long tunnel down there in which LEP exists. The magnets for LEP have been designed to steer little electrons and positrons. What we're going to need is completely new types of magnets to steer bulky protons. And so the design of that started being looked into. And by the 1990s, a way forward, it was becoming clear that it would be possible in principle to build such a machine. It was going to be very costly. It would require the 15 member states of CERN, as there were at that time, to agree that this was the way forward. The CERN's budgets would have to be cut back for doing almost anything other than focusing on the design and the build of the Large Hadron Collider. And Britain at that time were really playing the bad man of Europe. What's new? Because they were really worrying about value for money. And this became a potential showstopper in that if Britain said we're not going to sign our part of the check, the whole thing would have folded there and then. And perhaps the end of particle physics and that type of inquiry would have come to an end, and we would never have known anything at all about the Higgs boson. But then a couple of things happened. First of all, the science minister in Britain, a man called William Waldegrave, the constituency that he represents happens to be in Bristol, which was the town of Higgs's childhood. So that was a sort of interesting coincidence to try to exploit. And he was also unusually intellectually curious. And he issued a challenge to the particle physicists and said, look, if you could describe what this Higgs boson is all about on a single sheet of paper, maybe that would help me impress the Chancellor when he's setting the budgets for next year. And I will award vintage champagne as a prize. So we all entered this. I did. I didn't win it. But I did send him a note. I said, I find it a little bit disturbing, the idea that you can describe these profound ideas on a single sheet of paper. However, I said, I will take up your challenge if you'll take up the similar challenge from me, which is to describe on a single sheet of paper the Maastricht Treaty. That was the time when Britain was contemplating whether they were going to go into Europe with the euro and so forth. And there was this huge legalistic, impenetrable, jargonese-filled document called the Maastricht Treaty, which nobody could understand. Anyway, Waldegrave later said to me, we both failed the other person's challenge, I think is how he put it. But that got interest going in Britain, and people in Britain realized that, there's a Brit involved in this. Higgs, who's Higgs? And that, I think, again, is also part of the charm. Who's Higgs? That if this person had been named Einstein or Rutherford or Fermi or something, those are the sort of names that scientists have. But Higgs it's almost like a yeoman, a person who works in the field, a solid English worker from the centuries that have been working the land. And this sort of psychological feeling, if somebody called Higgs can do this, then you and I can do this. There was that sort of common touch to it in its way. And that's when my involvement, I suppose, began early on, the desire to try to help Higgs be a visible icon for all of this, and for him to be part of the whole publicity process, I suppose, which is certainly not the sort of thing that he was comfortable with anyway. And also, he hadn't worked in this since 1966. And that's how I came to sort of be interviewing him on the stage and trying to help him bring the story out, and where the beginnings of the idea of the book came. And part two ends when we've got to the point in the story where at last, after 48 years of trying and having finally built the Large Hadron Collider, seen that it does indeed work, and it's probably the biggest scientific adventure since the Apollo moon missions. I mean, it was on that sort of scale. It involved physicists from all the countries of the world pretty well, tens of thousands of physicists and engineers and technicians involved in building and designing the detectors at the experiments, building the Large Hadron Collider facility itself, a huge enterprise. And it ended up costing over here the analog of about 10 billion euros, spread among, of course, all the member states and things like that. And in the public's mind, this was all tied up with searching for the Higgs boson. So if you can imagine yourself as Peter Higgs, who in a state of naive innocence in 1964 have written these equations on a piece of paper, and now, nearly half a century later, see all of this activity based upon this idea, I don't quite know how I would handle that. And there I am interviewing Peter Higgs on the stage. And I remember the first time we opened it, and I tried to sort of lighten the thing. I said, so Peter, I said, 1964, you wrote these equations on a piece of paper, and 40 years later, there's tens of thousands of physicists. They've built this huge facility to look for the idea, and it's cost about 10 billion euros in total. If today or tomorrow you found a mistake in your arithmetic, would you tell anybody? I mean, it was a rhetorical question because we knew there was no mistake in arithmetic and there had been too many things done with it. But that was an example, I think, of the sort of pressure, because there was no mistakes in the arithmetic. the theory was completely solid, but you do not know whether the theory is right until you've experimentally tested it. And that is what sets Higgs apart from the pack, in my opinion, that only he had drawn attention to the fact that if this whole mathematical structure makes any sense at all, it means that there really is this weird field in which we're all immersed. And by analogy, your listeners are probably saying, well, what's a field? Well, you've heard of a magnetic field, like the Earth has a magnetic field which goes out into space. Electromagnetic fields, one has heard of. If you apply energy to an electromagnetic field, you can make it burst into light, because light is electromagnetic radiation, which in quantum theory becomes little bundles of stuff, photons. So by striking a match or just flicking a light switch, you can produce millions of photons just like that. Similarly with the Higgs field, if you can apply energy to it, you can produce the analogues of the photons, namely Higgs bosons. The difference, though, is one of scale. That, as I said, you can produce millions of photons just by flicking a switch. To produce even one Higgs boson is so difficult, you've got to have the whole infrastructure of the Large Hadron Collider smashing these particles together to make just one of these things bubble up. And it only lives for a fraction of a second, so you have to detect not it, but the decay products of it in the hope of capturing evidence for it. And to draw a further analogy, you might say, well, what's the relation between the Higgs boson and the Higgs field? Well, what is happening is that today we live in a very cold universe, and this Higgs field is like a placid lake, to make some metaphor. I say that we need this Higgs field just like fish need water. And by discovering the Higgs boson, it's analogous to the fish having discovered a molecule of H2O. What the fish need to know is how those molecules of H2O form the oceans. What we want to know is how those Higgs bosons form the Higgs field, and that we don't yet know. We just know that it is there because we've made one bubble up and reveal itself. But where the Higgs field has been in the history of the universe, back in the first trillionth of a second, the universe was incredibly hot, far hotter than anywhere even in the densest star today. And in that epoch, in that very hot condition, Higgs bosons were bubbling in and out of existence all the time. When the universe cooled, the Higgs bosons were just sort of condensed into this background placid environment. And so, if you like, they've been dormant for 13.8 billion years, until at CERN we were able to focus so much heat energy into a small spot. In that brief moment, we replicated that first trillionth of a second and made a Higgs boson bubble out and reveal itself again. So that is what we've done. We've been on a journey back in time in a certain sense. But the discovery was on the 4th of July. I was at a conference in a summer school in Sicily with Peter Higgs at the time. There had been a lot of speculation that a discovery might be announced later that year. Nobody anticipated it was going to be made in July, as it turned out. Peter and I were due to come back to the UK on the 2nd of July, when he received a phone call one lunchtime to say that there's going to be a big announcement at CERN, and he might be disappointed if he wasn't there. And we also learned that all living director generals of CERN had been invited to this. So it was quite clear. We knew that the experimental teams were going to make their annual reports. But at that moment, you knew that they're not going to invite all the past DGs to be there if the report's going to say, we haven't found anything yet. So Peter completely changed his travel plans and decided, rather than flying back to Edinburgh, he would go to Geneva. Well, he didn't have any Swiss francs with him. And also his travel insurance ran out on the 2nd because he thought he was going home that day. So all of those things, mundane things, had to be dealt with. So he and I were together at the airport in Palermo. I was going to fly back to England, and we now know, of course, Peter's going to fly to Geneva. And this we put out on Twitter with a rather misleading caption to give the impression that Peter was going to. But I said that I was flying back to England via Rome, and Peter was flying to Geneva, full stop, to give the impression that Peter was also flying to Geneva via Rome, whereas actually he was flying via Milan. The point being that any paparazzi who were going to descend on Geneva airport would come and meet the wrong plane, which indeed that bit worked. But the next day and the next day onwards, mayhem resulted. And the way that my second part of the book ends is what I call the 4th of July, with the absolute mayhem of the announcement, well, the excitement of the announcement. It's an exceedingly moving experience. I was in England watching on the internet, along with many other scientists, and you could sense not just the excitement, it was a superb atmosphere. I later learned that people had been queuing outside the CERN amphitheatre overnight, almost camping there to ensure that they got a seat in the auditorium. I mean, the DG had made a very profound decision. Apart from the former DGs and Higgs and people directly involved, the handful of people, the leaders of the experiments and so forth, it was like first come, first served. He wanted it to be an open event for anybody at CERN, not just the bigwigs. And so everybody was camping out to go in there. Peter Higgs was in the audience, and you could see on the television monitor, on the internet monitor that we were watching on, that when it suddenly became clear that indeed the particle had been found, and he was wiping tears from his eyes, as we were. And it was quite uncanny, because in that moment, something very profound had happened. A month before, when I had interviewed Peter Higgs, before we knew that the boson existed, though we strongly suspected it for many, many years, but we didn't yet know. This was the first time I'd ever interviewed somebody on stage. And by chance at the festival was a man called Jim Nocte, who in Britain is very well known as an interviewer. He's interviewed every politician of note in the universe. And I said to him just before I was going on stage, I says, Jim, I said, no, I've never done this before. How do you do interviewing of people on stage? He said, oh, it's easy. I said, well, it's easy for you. I says, but about me, I said, if you were going on stage now to interview Peter Higgs, what would you ask him? So Nocte thought for a few moments, and then he said, contextualize it. And I said, yeah, okay, what exactly do you mean by that? And he said, well, is all this stuff about the Higgs boson, is that just hype that's been created by the scientists and the media have gone along with it? Or would its discovery really be a seminal moment in human culture? And I thought, that's it. It would be a seminal moment in human culture. And the challenge now is to bring out precisely why and what it all means. And so that's how it started. So there I was watching the announcements on this, at CERN that day. And I thought, this is the moment. The epochs have changed. That up to this moment, we all speculated that the universe is like this. And now and for all time, we know that it's like this. And that is a profound change. That suddenly 2,000 years of searching from the ancient Greeks to the basic pieces of matter as to how everything is made had moved on, because by this we had found the proof that there is out there this sort of stage, the Higgs field, that determines these particles' masses and their properties that enable them then to do the stuff they do. So we have been looking at the players looking for the players for 2,000 years. And now at last we've found the stage that they're playing on. And that's what it amounted to in certain terms. So afterwards, Peter Higgs then had to do a 20-meter walk from the auditorium across to another room where all the world's science press were lined up. And it was absolutely mayhem. And I talked to the two CERN ladies who'd been assigned to helping him, one of whom she'd only been at CERN for 3 days. She had the responsibility for showing Higgs around. And she said to me, I didn't even know where the toilets were. So it was like that. And of course, the media wanted to know, have we got it? Have we really got it? And the two ladies and Peter Higgs all said, it was a frightening experience. That you had boom microphones stuck in your face, you had cameramen walking backwards in front of you. They walk very carefully, they're always just a meter away from you, but nonetheless, they're there in your face and thrusting these microphones in, and everybody wanting a picture and a quote and so forth. And somebody said, I now know how Princess Diana must have felt. It was quite an overwhelming experience. And it was as a result of that Peter, I think, the concerns that he'd had about being in the limelight and his reaction to the world media, that really crystallized it for him. And that's the end of the second part of the book, because the third and final part really is what happened next and so what. And the first chapter in part 3 is a quote from him, "Time to plan my escape." Because immediately there was speculation, will the Nobel Prize for 2012 go to Peter Higgs, and if so, who else? Well, of course, he knew the answer was no, because the Nobel Prize it was too late for that year's Nobel Prize. But nonetheless, the amount of media reaction there gave him a foretaste of what it would really be like, most likely the following year, when the Higgs boson discovery would really be at center stage. And so that is what then led to the famous event of Higgs's disappearance. And actually, the way that I structured the book was, I thought this part of the story was itself so dramatic and an example of his elusiveness that I sort of begin it as a sort of foretaste of the story, like often happens, that you see dramas on TV where you see something and then 3 months earlier they jump to that sort of thing. And it was the day when the Nobel Prize will be announced in 2012. And Higgs had this plan that he was going to be away. He wasn't going to be around. He told his colleagues that he was planning to go off to the north of Scotland. But then he had this insight that he didn't need to do that. He could just go to his favorite seafood bar about 4 kilometers away from his house in Edinburgh. And so he set off first thing in the morning and did that. And I described how it was, and he told me how it all worked. He went to the seafood bar. He doesn't have a telephone. He didn't know anything else what was going on in the world. Nobody knew where he was. The Swedish Academy delayed the whole process for half an hour because they couldn't find him. It's normal to contact the winners and alert them to the fact. But eventually they decided to go ahead anyway, and nobody knew where Higgs was. So at the end of his lunch, he then came back home. He said he didn't want to get back too soon, so he went to an art gallery to spend some more time. Already you may be thinking, like I was and still am thinking, why really did he do all of this? I mean, why disappear like this if what really drives you is fear of the media? Because what you are doing is creating an even bigger story. But anyway, that's what he did. And then he came back towards his house, and a car stopped, and a lady that he knew leant out and says, "Peter, congratulations on the award." And so he said, "What award?" Of course, he knew what she was referring to. But he got back home and went into his house. And then it was only later that afternoon on the radio news that he heard that he was sharing the prize with Engler. Engler's collaborator, Robert Brout, sadly had died a year or so before. So it was Engler and Higgs who shared the prize, which was awarded in December 2013. So the book sort of ends with what I call the glittering prizes. Peter's experience of the Nobel week. You're in Stockholm for a whole week. The Nobel Awards are obviously the highlights, but just one part of that week. And that was a very interesting story in its own right. I'd often wondered, I assumed that people wore suits, morning suits like you do at a wedding, but no, they are dressed up in the gear from the time of Alfred Nobel. Nobel lived in the 19th century. And you have almost like costume from his time. And so Higgs said, we went to the first day there, we went to the tailor's and we were fitted for this costume. He says, even getting into the shirt was almost like an exercise in topology. It was so difficult. But anyway, he won the prize and he was awarded the prize. And then we come to the reaction after the Nobel. And one of the things that I had noticed was the reaction of the public to him. The very first time that I had interviewed him on stage was before the boson was discovered, and you announce Peter Higgs, and the audience applaud, and they're pleased to see him, and the applause lasts a certain amount of time. You sort of know in your head how long it's going to be. Then the boson was discovered, and the next time I interviewed him was actually in Edinburgh, his hometown, just after the boson's discovery. And again, I came on stage, blah, 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 introduced Professor Higgs, the audience applaud, and the applause just kept going on and on. And I thought, this is their boy. This is for them. They can applaud for an hour and go home happy. It was a very strange feeling like that. The next time I interviewed him in Edinburgh was after he'd won the Nobel Prize. And you might have thought that the applause this time would have been even greater. But no, it was in a strange way more formalized and back to normal. Not because the novelty had worn off, I think. It was that back the year before, just after discovery, Peter Higgs was still, if you like, owned by Edinburgh. This was their person there that they were recognizing and they would applaud forever. A year later, Peter Higgs was a Nobel laureate and was owned by the world. It's a very strange transition. And I think psychologically for the person, it's a very profound thing. And talking with him at length, and I try to bring this out in the story. I mean, I'm not a trained psychologist, but I think it is clear that it is very hard not to have imposter syndrome when you're selected into a group like that, along with the greats like Rutherford and Einstein, let alone if your personality is such that you don't like the limelight. And so I end up with the conversations that we then had a year or two afterwards, which is really, so what does this all mean? What is the future of physics? What do we do next with what do we really want to understand about the Higgs field and the Higgs boson? Where do we go from here? And so I end up with a look towards the future. Whether any of that will turn out to be true, well, we maybe have to wait another 48 years to find out, but that's how it all worked out.
This is truly a fascinating story and just so multifaceted. And I was wondering, just as your title suggests, Peter Higgs is quite an elusive character. How did you manage to persuade him to write a book about him?
I suppose you have to ask him that question. I decided that this was something that I wanted to do. I had written a book called The Infinity Puzzle about 10 years ago, which was a detailed history. This was just before the boson was discovered. And this was the history of particle physics post-war, really, for my part, to educate myself on what all this Higgs business was about. And this became a book that the Nobel Committee studied when they were trying to assess various claims for priorities and who had done what and so forth. So that was back in 2012 I had done that. And Peter had obviously enjoyed that because he did a very generous thing that when I was interviewing him on the stage that very first time, it was actually at a literary festival. And so copies of my book were on display. And after the talk with Higgs, of course, the audience will come up and they all want Peter's autograph. And so he said, he was happy to give people his autograph so long as it was on the inside cover of my book. And so I've never had such a long line of people queuing up to buy copies of one of my books as I did on that day when Peter Higgs was there. So obviously he liked what I had done. I mean, he knew me personally, but respected that I was able to assess these things in a fair way. And that is, I suppose, why he was happy to do this with me. That said, it was a very difficult time. I mean, we are now dealing with somebody who is into their 90s, and we were doing it long distance over the telephone. And he has very strong views on what he would want to say and want not to say. And of course, this was my book writing about him, not his book writing about him. So it was not easy. And I had to make a lot of decisions. Along the way, he told me some things which I thought were too personal to go into a book, because it's very easy when you're chatting with somebody that you know to say things that you probably don't want to be on the record, even though they are on the record. But equally, I also had some surprises about the science. And two things. My feeling about the disappearing acts on the day that the prize was awarded, I don't have an answer, but I do have a question I keep asking myself. Bearing in mind the fact that my closest friend, in this case Michael Fisher, had got very strongly tipped to share a Nobel Prize, which he then was excluded from, and was devastated by the fact that I am now in the situation where the whole world is saying that I'm a shoo-in for the prize this year. And I can't get the idea of my friend's experience out of my mind. If that were to happen in my case, how would I handle it? Well, speaking personally, I would want to have some time on my own to reorient myself, and maybe disappearing at the time might be a sensible option. So that was one thought that came to me. The other surprise that I had was a very deep one in the scientific sense. And I'll try to say this in a way that isn't going to be too difficult for the audience. But Peter wrote these papers in 1964, the two short papers, along with these other 5 people at the same time. It was 2 years later when he wrote a big paper during a year's sabbatical at the University of North Carolina. And it was in that big paper where he included what you might call the DNA fingerprint of what became known as the Higgs boson. And indeed, it was in that paper that the key way of identifying it was spelled out and was used by the experimentalists to identify and prove the existence of the particle. And that is why I felt, and I think most of my colleagues do, that that's what set him apart from the rest, that he had shown the experimental way forward. I said, no, the difference between a theoretical physicist and being Shakespeare is that Shakespeare, he wrote many sonnets and many plays. There isn't just a one and one only. He might have changed a few words in them, and they would have still been wonderful works of art. Peter Higgs wrote some equations down. If you change just one symbol, the whole meaning would be changed and they wouldn't work. The key thing that distinguishes the great piece of mathematical structure is if nature reads it. And that is where experiment comes in. It's an experiment that decides what is real and what isn't. And the Higgs boson was the way that nature showed us that what all was being done was indeed correct. And so that's why I regarded that as so important. And then Peter, on one occasion, he was quite agitated, saying that I had actually not really understood the reasons he'd written this paper in 1966. And he spelt out the reasons why, and I rewrote part of my book. And it was and still is quite a shock to me. Basically, he said this: people, the few people who had taken any note of these short letters that he'd written in 1964 were not all convinced by them. They thought there might be technical errors and so forth. So his goal in 1966 was to write a paper really explaining the whole mathematical foundations of this theory. So like a legal document, it would all be spelled out there. And he did that. And then he read it and he thought, this is exceedingly technical. Maybe I also need to include some sort of simple pedagogical example. And so he inserted a section in the middle of that paper to give a sort of illustrative example of the ideas he was talking about. And in that section, there happened to be some equations which turned out to be the key ones that the experimentalists later used. The surprise was that Peter said to me that it was only after the Higgs boson was discovered that an experimentalist told him, that, oh yeah, we use this. It wasn't until then that he himself realized that he had provided the way for experiments to do this. And I was absolutely astounded, because basically he said that he'd written this, what it amounted to is he'd written this theory down in 1964, and 48 years later, experimentalists produced the proof of the whole theory by using his paper, and he himself hadn't until that moment realized the importance of what he had done in his paper. And so I think there's something very profound there. But that was a shock that I had. If I have a scoop in science, that it is.
So then, what questions you still want to address? What did you discuss with Peter Higgs? Of what do you want to find out in a wider sense in a physics?
Well, two things. I mean, Peter made a very good point, which I say in the book, and I would say to any listeners. He said he was very worried that there'd been so much emphasis placed on the Higgs boson with regards to the Large Hadron Collider. I mean, he had been used for many years by the community of physics to help promote this quest. But in the public's mind, the Large Hadron Collider was totally associated with the Higgs boson, whereas in reality, it does much more than that. But Higgs said, in the public's mind, they feel that it was all built to find the boson, and now it's been found, so the public will say, why don't you turn it off? And he felt it was important that, one realize and demonstrate that the Higgs boson is one piece of a very big set of things that the machine, the LHC, can look for. But of course, it is so singular that it makes huge headlines, and the LHC will make discoveries, but nothing like this. I mean, I would say that the discovery of the Higgs boson, its implications in the physical sciences are as big as a century earlier Rutherford's demonstration that of the nuclear atom was. And you don't make discoveries like that every day. So there's that. So, but at a more pragmatic level, what are the immediate things that you want to do? We've discovered the Higgs boson. That demonstrates that the Higgs field exists. What do we know about the Higgs boson? Well, it shows that the Higgs field doesn't have any sense of direction, which is what the theory predicted. We know how much energy it takes to make it bubble up and produce Higgs bosons, and that's about it. What we don't know is how these bosons actually condense to make this field. And so the simplest and first step would be what is now hopefully going to happen at the Large Hadron Collider is if you had higher intensity beams, then there's a chance that when you collide, you might produce two Higgs bosons in a single collision. And if you're lucky, those two bosons might interact with each other before they die, and you could detect that in your detectors. And so you would get the first insight into how bosons interact with one another and make the first step into building up this ocean, which we call the Higgs field. And that hopefully should be possible in the next few years, because the LHC has been sort of upgraded. The beams are brighter, and effectively the collisions at slightly higher energy. And so that hopefully we will begin to know. The longer term, the LHC is looking far beyond a horizon that we've ever been able to see before. And what is out there at the moment, only nature knows. And if I was really confident that I knew what it was, I wouldn't be having this conversation. I'd be writing that paper down myself and hoping it didn't take 48 years to prove it right.
So essentially, it's all just the start of the story then.
In a way that I said that the discovery of the Higgs boson is the end of the beginning, not the beginning of the end.
Well, this has been a truly fascinating glimpse into this extraordinary story. So, can you tell us, what are you currently working on and what will be your next project?
Well, the short answer is taking a rest. Well, what I have been doing just for my own amusement is writing a series of short essays called 7 Lucky Numbers. So I thought, why do we believe the number 7 is lucky? So I chose to have 7 lucky numbers. So I've got 3 essays, because 3 is also a lucky number. I have 3 essays on each of 7 different topics: integers, irrational fractions, pi, E, exponential. Everybody knows about that because of COVID, I suppose. Nothing, infinity, and imaginary numbers. So there's the 7, and I've just sort of done that for amusement. But what I shall start with, and I mean, hopefully I'll get that out and published. It'll just be a small, easily readable book, nothing like Elusive in its profundity. But what I do think I might work on, I've got an idea in my mind that I'm calling Destroyers of Worlds, which is really the origins of the nuclear age, the birth of the nuclear age, from the original discoveries that led to the obviously that led to the atomic explosions at which Oppenheimer uttered those famous words. Now we become destroyers of worlds. But then what happened next? How did it come about that nuclear power, as of immediate post-war, was going to be the great way that was going to solve everything, and now it turns around that people think quite the opposite. And destroyers of worlds might have more than one meaning. It might be that if we don't use nuclear power, then we're going to destroy the world by killing off the climate. I don't know yet where this will lead, but it's a vague area that I want to know more about, and hopefully it will crystallize enough that I might write about it. We'll see.
That sounds super exciting. So where can our listeners find more information about your work and also your book?
Well, about my book, I suppose, I hate to say this, but if you go to Amazon, you'll find the book on there. What I like to do, well, I hate to say this, I love bookshops. I love local bookshops, and I love supporting local bookshops, because if we don't do that, then bookshops will die. So probably go to your local bookshop and ask them, do they have Elusive by Frank Close, which is coming out in Europe on the 7th of July. And if they don't, why not? Or you could go to Amazon and get it from there. And I suppose from that, you'll then find out about other books and things that I've done. In the last 2 books that I wrote were centered in the immediate, Second World War and post-war period, of 2 physicists, one of whom definitely was a spy. That was Klaus Fuchs, and another one, Bruno Pontecorvo, who was a great physicist who may or may not have been, but he disappeared through the Iron Curtain in 1950 and off the face of the planet for 5 years. So the book about Pontecorvo is called Half-Life, and the book about Fuchs is called Trinity. So those are the last 2 books that I did.
Excellent. Well, thank you so much for joining me today.
Thank you.